Oscillatory motion is divided into spiral parts between them. What is oscillatory motion? Oscillatory motion is defined as the to and fro motion of the body about its fixed position. Oscillatory motion is a type of periodic motion. Examples of oscillatory motion are vibrating strings, swinging of the swing cat. This is an animal example of an oscillatory motion. Result Hooke's law. Hooke's law states Fx equals thus Kx. Fx is the restoring force. It is always directed toward the equilibrium position. Therefore, it is always opposite the displacement from equilibrium. K is the force or spring constant. X is the displacement. What is the restoring force for a surface water wave? Restoring force in the spring-based system. Point in A, the block is displaced to the right of x equals 0. The position is positive and the restoring force is directed to the left or negative. We can see the picture of the spring based when the block is displaced to the right of equilibrium. The force exerted by the spring acts to the left. Point in B, the block is the equilibrium position. X equals 0. The spring is neither restricted nor compressed, and the force is 0. We can see the picture of the spring visit. When the block is at this equilibrium position, the force exerted by the spring is 0. Point in C, the block is displaced to the left of x equals 0. The position is negative and the restoring force is directed to the right or positive. And we can see the picture of the spring visit. When the block is displaced to the left of equilibrium, the force exerted by the spring acts to the right. Differential equation of motion using F equals ma for the spring. We have ma equals thus kx, but result that acceleration is the second derivative of the position. A equals d quadrat x slice dt quadrat. So the simple force equation is an example of a differential equation, and d quadrat x per slice dt quadrat equals thus kx, or d quadrat x the slice dt quadrat equals thus k slice mx. An object moves in simple harmonic motion whenever its acceleration is proportional to its position and has the opposite side to the displacement from equilibrium. Acceleration. Point 1. Note that the acceleration is not constant, unlike our early kinematic equation. Point 2. If the block is released from some function x equals a, then the initial acceleration is dash ka says m. But as it deviates drop 0, the acceleration falls to 0.3. It only continues past its equilibrium point because it now has momentum or kinetic energy that carries it on fast x equals 0.4. The block continues to x equals dash a, where its acceleration then becomes plus ka says m. Analysis model, simple harmonic motion. What are the units of k slash m in a equals d quadrat x slash dt quadrat equals dash k slash m x. Point 4. A typical way to solve a differential equation is to simply search for a function the state space the requirement indicates that its second derivative yields the negative of itself. The sine and cosine function meet this requirement. As M graphical representation. A solution to the differential equation is xt equals a cos omega t plus psi, when a omega psi are all constant. Amplitude or maximum position in either positive or negative x direction. Omega when akar k slash m. Psi constant or initial phase angle. A and psi are determined by initial condition. When remember the Faraday and frequency are T equals 2V slash omega, or F equals 1 slash T equals omega slash 2V. Consider the energy of M oscillator. Point 1. The spring force is a conservative force, so in a frictionless system the energy is constant. Kinetic energy, as usual, is K equals quadrat equals 1/2 m omega quadrat a quadrat sin quadrat omega t plus psi. Point 3. The spring potential energy, as usual, is U equals 1/2 kx quadrat equals 1/2 ka quadrat cos quadrat omega t plus psi. Point 4. Then the total energy is just A equals K plus U equals 1/2 ka quadrat, when A constant. This is the formula form of motion equation for simple harmonic motion. And here we can see an example of simple harmonic motion. Next, simple pendulum. Point 1. The forces acting on the above are the tension and the weight. Point 2. T is the force exerted by the steering. Point 3. Mg is the gravitational force. Point 4. The tangential component of the gravitational force is the restraining force. Point 4. Result that the tangential acceleration is A1 equals R A equals L A equals L d quadrat theta slice dt quadrat. Point 6. This gives under differential equation d quadrat theta slice dt quadrat equals dash n g slice L sin theta tak terhingga dash n g slice L theta or 4 small theta. We can see the picture of the pendulum bezier. When theta is small, a simple pendulum motion can be modeled a simple harmonic. A simple harmonic motion about the equilibrium position theta equals 0. And even